Hello class, I'm Dr. Yang and welcome to cs370 operating systems. Alright, enough with theory of operation of Semaphore. Let's talk about the real world stuff. As I said, the Semaphore was invented very early, even before the invention of Unix. So there are a lot of history and a lot of different versions of implementation, different interfaces. First of all, the use of Semaphore is discouraged. But in case if you have to use Semaphore, especially in Unix systems, there are a lot of options. So therefore, you get confused because there are a lot of options. So I'm going to clear things up a little bit over here. So UNIX Semaphore variants. You have a System 5 Semaphore and POSIX Semaphore. And System 5 Semaphore is the old one. Obviously, I discourage the use of Semaphore in favor of condition variable. But if you have to use it, then don't use System 5 Semaphore. Okay. So here's the variants of UNIX Semaphore. In many Unix systems, Semaphores are available in two different ways. One is known as System 5 Semaphore, and the other one is POSIX Semaphore. And this System 5 Semaphore is the old one. And the System 5 Semaphore was developed even before threads. So if you're sharing memory and you want to synchronize between processes, one way to achieve the synchronization is to use a semaphore that's part of the System 5 inter-process communication suite. It's a part of the System 5 IPC suite. And actually there's a command. Many Unix systems you have this IPCS command, and it will list the resources associated with IPC. And the thing is, this System 5 Semaphore is entirely system call based. So it's a high cost. It's a slow. And the interface is a horrible interface. So don't use it. If you have to use a semaphore, then use a POSIX Semaphore, because this is more recent and so new, fast, and lightweight. In case of Linux, it's a part of the NPTL, and therefore the weight overhead is far less severe. Right. And there are two types of POSIX Semaphore. So one type is named, the other type is unnamed. The thing is, the operations of named and unnamed semaphores are exactly the same, and they both have P and V calls, and they behave just like the same way. The only difference here is the named semaphore is associated with file name entry, such as this. So you can utilize the file system naming facility to locate and share this POSIX named semaphore among threads and among processes. Okay. On the other hand, unnamed semaphore doesn't have associated file system entry, and instead you just share the pointer of this semaphore instance. So this is a System 5 Semaphore interface. I said don't use it. So it's old interface, and if you're curious, read the main page for details. So it is incredibly complicated, not just to use it, but to set up. So there are a lot of indirection going on. This semop here is the one that you actually increment or decrement semaphore, but it requires semaphore ID. You can get this semaphore ID by using this key. Okay, you can get this key by converting this path name to key first. So because this is a system call based interface, and also you have this array of semaphores. It's not just one semaphore, it's an array of semaphores. You need to specify what kind of operations to perform on each of the semaphore. So it's crazy, it's complicated. And you have this miscellaneous operation system call as well. All right, POSIX Semaphore. So we're talking about this. Let's talk about unnamed semaphore first, because this is easy, and probably if you're going to use a semaphore to synchronize among threads, not among processes, this is the one that you probably use. So this is an init function, and this is a p operation, semWait, and semPost is v operation, increment by 1. So very easy. Okay, and obviously the init function comes with this value, initial value that you can specify here. All right, named semaphore. The operations are the same. Okay, so you have wait and post. This is a p and v operation. Because this is a named semaphore, you can actually use the file system to name the semaphore. So this allows multiple processes to access a semaphore. They have to share the semaphore. You can create this entry by calling this open. The file system entry can be created just like creating regular file, and you can open the semaphore using this function. Okay, you can close. The thing is, the semaphore entry persists. Okay, so opening and closing, just like opening file and closing. After you close the file is still in the file system. So if you want to remove the file, in this case, the equivalent idea is to remove the named semaphore entry. You actually have to delete this entry. You can delete that file system entry by calling this semunlink. All right. So far, we looked at some of the technicalities of semaphores. Let's come back to talking about the utility of semaphore. Obviously, in the beginning, I talked about the semaphore as the alternative of condition variable. So you may wonder, okay, which one is better? Are they the same? So, in theory, yes, semaphore and condition variable are functionally equivalent. You can actually prove it. How do you prove it? Let's say you have condition variable and mutex, and let's say you have a system that only has semaphore. The equivalence proof can be done by showing that you can create semaphore out of condition variable, and also you can create condition variable and mutex using semaphore. The mutex is a trivial, so just cross this mutex out. So basically, if you can show that you can make condition variable out of semaphore, then basically that's the end of the proof. And you can do it. In fact, implementing semaphore from condition variable is rather trivial, very easy. So semaphore has two operations, P and V. So you want to construct this semaphore thing out of condition variable, and it's too easy, actually. So this is easy, but it turns out implementing condition variable from semaphore is extremely tricky. All right, so this direction, this is hard. Okay, it can be done. It can be done. So they are equivalent. Condition variable and semaphore, functionally they are equivalent, but constructing condition variable out of semaphore is hard. And the whole point of that exercise of constructing condition variable out of semaphore is that it is tricky and difficult to do it. So that means, not in theory, but in practice, it implies that condition variable is more versatile. The semaphores are too restrictive, and that is one of the reasons why use of semaphore is discouraged and use of condition variable is recommended. I'm going to drive home the point by this quote from the inventor of semaphore. His name is Edgar Dijkstra. So let's read the quote. During system conception, it transpired that we used the semaphores in two completely different ways. All right, this system refers to the operating system. And part of the development was the use of Semaphore, the invention of Semaphore and the use of Semaphore. Right, let's go back to the quote. During system conception, it transpired that we used the semaphores in two completely different ways. The difference is so marked that looking back, one wonders whether it was really fair to present the two ways as uses of the very same primitives. On the one hand, we have the semaphores used for mutual exclusion. On the other hand, the private semaphore. Obviously, the semaphore used for mutual exclusion refers to the binary semaphore. And the private semaphores are the semaphores that counts number of resources. And this was from the inventor of the semaphore, and he recognized early on that the usage is so different. All right, let's think about the semantics of semaphore. Semaphore is stateful. Compared to condition variable is stateless, is memoryless. But semaphore is stateful. Obviously, it has internal counter. That's the defining feature. And the counter remembers how many times P and V's have been called. Okay, that's important distinction. So the program using semaphore has to construct synchronizing strategy using atomic counter. Whatever problem, whatever thread synchronization problem that you're trying to solve, if you're using semaphore, if you're going to use semaphore, you have to somehow cast that problem that you're trying to solve. Whatever problem it is, you have to transform that problem into number counting problem. That is sometimes easy, but usually it's not easy. V, the increment operation, always increases counter. So the number of V call matters. You cannot say this when you're dealing with condition variable signal. Condition variable signal doesn't remember anything. So at the point of signaling, if there's no waiter, then the signal gets lost. But semaphore, the number of V calls gets remembered. So you have to write your code to call V precisely. No more, no less, you have to call exact number of V's. So the moral of this story is don't use it. Don't use semaphore, especially if you're given the option for condition variable and mutexes. Right. Then you may ask, is there a case where semaphore has to be used? Okay. The answer is I cannot honestly think of any case in usual applications. But there are some fringe cases where semaphore or sort of semaphore-like approach, I should say, is more appropriate, and you can find it in kernel. And sometimes you have to do some kind of naked signaling. So naked signaling means that you're calling this signal outside of critical section. And we talked about why that's dangerous. The reason is the signal can be lost. But in kernel, especially when you're writing interrupt service routine, ISR refers to interrupt service routine, then it is impossible to block essentially, because the ISR executes in borrowed context. When the interrupt happens, the interrupt service routine will be invoked by processor's interrupt delivery mechanism by interrupting whatever program, whatever thread that was executing at the moment. So some kind of random process and random thread gets interrupted. And that's the reason why you cannot block, you cannot victimize that thread that just happens to be there. Technically, it's called interrupt service routines are executing in the borrowed context, because interrupt service routines executing right now is actually borrowing the context of the victim thread or process. So if that's the case, then it is not only unfair but dangerous to block. So, but the thing is, let's say there's a network packet arrived, and you have to unblock program that's waiting on that packet. Then you have to signal that process or thread. And the thing is, you cannot create this blocking critical section. So that's why you have to do some kind of naked signaling. And to get around this situation, what you can do is you can use a semaphore or semaphore-like approach, because in kernel, it's usually that all the internal components that actually implements the semaphore or condition variable or mutexes are available. In kernel, you have all the nuts and bolts are available. So I should say it's like a semaphore-like approach. But when you have to do some kind of naked signaling, then you can use a semaphore. And you can see from this example. Okay, let's go back. All right, so if you look at this, you didn't call P inside this critical section, but over here, full slot V, this V call can be safely called outside this critical section. And this is safe because the V operation itself is atomic. All right, we are almost done talking about thread synchronization. So the next class will be the thread internals and the internals of the synchronization primitives. But before we finish, let's take a step back and learn about the taxonomy of synchronization primitives. All right, the Mesa semantics and Hoare semantics. We already talked about this Mesa semantic, and the taxonomy of these synchronization primitives. I'm going to use this whiteboard here. Taxonomy of synchronization primitives. On one camp, we have a mutex and condition variable. And over here, we have a semaphore. And these are two big alternatives. And mutex and condition variable, there are actually some variants here, different semantics. And people call these types of synchronization primitives as monitor. This is another name. Monitor is the name that refers to a collection of synchronization primitives that more or less behaves like the mutex and condition variable that we learned so far. So you have monitor and you have semaphore. And the monitors can come in Mesa semantics, and the other one is known as Hoare semantics. And I should say this, the Mesa semantics, the monitors that follows Mesa semantics are the one that we learned and used by most operating systems. So it includes POSIX, C11, and also Java and C# and so on. So this Mesa semantic monitor are most widely available. And there is a monitor known as Hoare semantics. And the Hoare semantics here, going back to this PowerPoint slide, the Mesa semantics, when you're signaled and you're woken up, then you move from wait to ready state. And after that, the scheduler will later decide which thread to run, and then if you get picked, that is the moment that the thread actually gets executed, making transition from ready to running state. And this was the Mesa semantics. Hoare semantics, the signal is different. Signal actually schedules and executes the woken up thread right away. So there is no transition from wait to ready. It makes transition from wait to running state. So this is a different behavior, different semantics. Right. And the thing is, The Hoare semantics is not widely used, despite the fact that you can use the analysis of concurrent algorithm. So what it means is sometimes you want to actually prove. You want to prove your concurrent algorithm works correctly. If your code is written using the monitor with Hoare semantics, it's sometimes easier to prove. But in practice, virtually all production system uses Mesa semantic. Okay. And by the way, there is a whole world of completely different kinds of thread synchronization approach, but they are all experimental and it's not widely used. They are more theoretical. So one example is CSP, communicating sequential processes. So this requires completely different languages and completely different threading model.